In the problems at the bottom of the page, we're using the second derivative test to find points where we have relative maximum, relative minimum. And so to do that, I need to have both the first derivative and the second derivative calculated, so that's what I've done in advance on this page to save a little time. And these are the same derivatives as before, so we've already gone through this process. So in the first problem, the first step is to first solve where the first derivative is equal to 0, and I do that by factoring. This factors into 3x times x minus 2 equals 0. This thing does. And so that means that x will be 0 or x will be 2, are the two critical values. And the second derivative test says that I can check these by plugging them into the second derivative formula. So f double prime of 0 is negative 6, and f double prime of 2 is positive 6. And so that means, as far as the shape of the graph goes, when x is 0, a negative second derivative means that my graph will be concave down, and when x is 2, a positive second derivative means our graph will be concave up. So if I can visualize that this negative second derivative means I have this shape, and a positive second derivative means I have this shape, well, the fact that this is a critical value and has this shape means that it's a local maximum. It has to be a high point if you're concave down and have a critical value there. If you're concave up and have a critical value, then you must be at a bottoming out point. You must be at a local minimum. So that's the conclusion of the second derivative test. So I have a relative max at the point 0, whatever the y-coordinate is, and I have a relative min at the point 2, comma, whatever the y-coordinate is. Don't forget the y-coordinate of any point on the graph is going to come from the original formula. So when x is 0, that's easy to figure out. That's 6. And when x is 2, this is 2 cubed. 8 minus 12 is negative 4 plus 6 is 2. So I have 2, 2. So that gives me both the x and the y coordinate of a relative max and a relative min. If I had lots of critical values, I could do that for each one, and any one that I get a definite concavity reading for, I'll be able to tell whether it's a relative max or relative min. In the second problem, I go through those same steps again. So the first thing is to find my critical value. So 8x cubed minus 24x equals 0 happens when x is 0, or x is the square root of 3, or x is the negative square root of 3. Again, we can just factor and find those three values. The second derivatives, give myself a little break here. The second derivative at 0, my second derivative formula is here. So obviously the second derivative is negative, it's negative 24. So I'm just going to say negative. I'm not going to try to calculate these. It's getting to the point where it's not any point to it. When I put the square root of 3 in, the square root of 3 squared is 3, so that's 24 times 3 minus 24. That's certainly positive. And f double prime of negative square root of 3 is going to be exactly the same thing, whatever that is, but definitely positive. And so I can visualize in my picture that when x is 0, I have a concave down graph, just like I did here. And so concave down and a critical value means I have a relative max. So I have a relative maximum at the point 0, comma 5. Again, my y-coordinate here is just coming from the f of x formula. That gives us our y-coordinates. And we have relative minima. There's two of them. There's one at the square root of 3, whatever that y-coordinate is. That y-coordinate is going to come from putting the square root of 3 in here. And so this will be 2 times 9, 18, minus 36 is negative 18 plus 4, and plus 5. So I think that's negative 13, but you can check that. And that'll be the same thing I get when I put in negative square root of 3. You check. So I think it's negative 13, but you might want to check that. Okay, and then the last one, we are first finding where the derivative equals 0. Whoops, didn't need to write that. In the third problem, we had pretty complicated first and second derivative, but it's pretty easy to, again, remember that finding out where something is equal to 0, if it's written in a fraction form, is really just finding out where the numerator is 0. And so the numerator of this is equal to 0 when x equals 5 or x equals negative 5. So even though the derivative itself is a big hairy mess, this part can be solved very easily. Setting this equal to 0, we get x is 5 or x is minus 5. And so we can plug these two numbers into the f double prime formula, and this is where it's nice to have simplified the numerator in the derivative of the derivative. It comes out kind of bad, as we saw, but then if we simplify it into these factored pieces, it makes it really easy to plug numbers in. So f double prime of 5, for example, this part is negative, it's negative 70. This is 75 minus 25, so that's positive 50, and that's positive 50. The denominator is always positive because it's raised to the fourth power, so I don't even care what it is, it's positive. So I have a negative number times a positive times a positive. So altogether that's a negative value. So I know that at x equals 5, the graph of f is concave down, and so that means I will have a relative minimum at x equals 5. And then whatever the y-coordinate is, we'll find out in a minute. F double prime of negative 5 is going to be positive for the same kind of reason. Negative 4 times negative 5 is positive 70, so I have positive times positive times positive, and divided by positive. So if I just check all those pieces, I see that I have positive, 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 so I get a positive answer. And so that means that the graph is concave up when x equals negative 5, so that means I have a relative maximum. Wait a minute. Concave, sorry. I'm not paying attention to what I'm saying. So this is a relative maximum, and this is a relative minimum. So remember, the idea is that this value, sorry, I was forgetting which one I had checked first. This f double prime 5 being less than 0 means that our graph is concave down, so it has this shape. A graph with that shape, you're looking at a maximum high point. When the second derivative is positive, then the graph has this shape, and so you're looking at a relative minimum. So the y-coordinates come from just plugging in the x's into this formula. So putting 5 in for x, we have 35 on the top, and we have 50 on the bottom, 25 plus 25. So 35 over 50 is the same as 7 over 10. And when we put negative 5 in, we hit negative 35 over 50, which is negative 7 over 10. And so we know that the high points and low points of this graph occur at those points.